Welcome to the deep dive. Today, we're getting into something pretty cutting edge. How do we get AI agents not just working alone, but working together? Like truly collaborative teams tackling really complex stuff in the real world.
Exactly. And we've got a great guide for this, really comprehensive review paper. It's called Multi-agent Embodied AI, Advances and Future Directions.
Right. This is the one by Zhaohan Feng and a team from several Chinese universities and labs. Gang Wang is the corresponding author listed.
That's the one. So think of this chat as, your fast track to understanding this whole area. We're talking multi-agent embodied AI, what it is now, where it's likely going, and honestly, why you should care about it for the future of AI.
Okay, sounds good. So our mission then is to unpack the core ideas, look at how we got from single agents to these multi-agent setups, and flag the big challenges and opportunities.
Precisely. We'll cover the foundations, the single agent stuff, then dive deep into the multi-agent world and wrap up with the hurdles and what's next.
All right, let's start at the beginning. Embodied AI. What exactly are we talking about here? It's not just algorithms running somewhere, right?
No, not at all. It's about AI agents having actual physical bodies, things that let them, interact with the world around them.
So they sense things, perceive their environment.
Right, through sensors. Then they think, they make decisions, that's the cognition part, and then they act. They do something in the world. And crucially, they adapt based on what happens.
The paper mentions this isn't totally new, that even Alan Turing back in the 50s hinted that real intelligence might need this kind of sensory physical experience, not just symbol crunching.
That's a really important point, and it connects to ideas like embodied cognition theory from the 80s, which basically argued that our thinking is deeply shaped by our bodies and how we interact physically.
Which is quite different from a lot of traditional AI that's more abstract, right? Less grounded in physical interaction.
Absolutely. The paper calls it the perception, cognition, action cycle.
Yeah.
Sense, think, act, see what happens, sense again. It's this continuous loop. That's how they learn and adapt.
Okay, so the paper breaks down embodied AI into three key things. First is embodiment itself, the physical form.
Yeah, the body. And it's super diverse. Could be a humanoid robot, could be a self-driving car, a drone, a factory robot arm.
Anything that senses and acts physically. Got it. What's the second?
Intelligence improvement.
Right.
This is where things like large multimodal models come in. They help the AI learn continuously, understand language, adapt quickly, even with just a few examples, that kind of thing.
And the third aspect, this is where it gets really interesting. You mentioned the generative models, like LLM.
Exactly. Large language models are turning out to be crucial. They help the AI understand instructions in plain English, for instance, and connect that language understanding to the physical actions needed.
The review really stresses this isn't just about sticking existing AI brains into robot bodies. It's described as a co-evolution.
Yes, that's such a key insight. The AI, the body, the environment, they all influence each other. Developing AI for a drone is different from developing it for a robot hand because the physical constraints and possibilities are totally different. It might lead to fundamentally new AI designs.
Okay, so that's embodied AI. Now, building on that, the paper talks about multi-agent systems, or MAS.
Right, so now we're talking about multiple autonomous agents. Each one can kind of think for itself, but they operate together in a decentralized way.
And that gives advantages like scalability, handling failure.
Yeah, scalability, fault tolerance, adaptability. If you have a complex task, sometimes breaking it down among multiple agents is just much more effective and robust than relying on one super agent.
So what makes something a multi-agent system? The paper lists things like autonomy.
Right. Each agent acts independently to some degree, decentralization, no single boss.
They need to communicate somehow.
Usually, yes. Inter-agent communication is key. And typically, they only have access to local information, what they can sense nearby.
Plus dynamic adaptability. They can change what they're doing collectively.
Exactly. And what's really changed MAS research, according to the paper, is the rise of learning-based methods, especially multi-agent reinforcement learning, MARL.
And LLMs again, they're popping up everywhere.
They are. Integrating LLMs is helping with communication between agents and also with higher-level reasoning, like deciding on a team strategy.
Okay, so before we jump fully into the multi-agent complexities, the review covers single-agent embodied AI first. This area is more mature, right?
Yeah, there's a lot more foundational work there. They break it down into classic control and planning versus the newer learning-based stuff.
Let's touch on the classic methods, constraint-based approaches. What's that about?
Basically, you define the goal and the rules of the world as logical constraints, like don't collide with obstacles, reach the target. The agent's job is to find actions that satisfy these constraints.
But the paper mentions limitations, like it's more about if a solution exists, not necessarily the best one, and it struggles with complex sensor data.
Precisely. They can get bogged down with high-dimensional inputs. Then you have sampling-based methods.
Like RRTs, rapidly exploring random trees. How do those work? In simple terms.
The idea is to explore the possible moves randomly, but efficiently. Instead of checking every single possibility, you build a kind of branching tree of feasible paths just by sampling points in this space. It's great for navigating complex environments without needing a perfect map up front.
Makes sense. And the last classic type, optimization-based.
Yeah, here you model the goal as a mathematical function. You want to minimize travel time, maximize smoothness, whatever. Techniques like model predictive control, MPC, or optimal control, OC, fit here.
The review has that cool example of aggressive drone flight planning, even allowing minor collisions, cutting task time by almost 60%. That's impressive.
It really shows the power of optimization when you model the problem well. Okay, now shifting to the learning-based side for single agents.
End-to-end reinforcement learning gets top billing here. They call it the ultimate pathway.
They do. The idea is the agent learns a direct mapping from what it perceives straight to the action it should take, all through trial and error. It's shown great success in controlling things like drones, robot legs, self-driving systems.
But if it's the ultimate pathway, why do we need the other methods? What are the catches?
Well, end-to-end RL can be incredibly data hungry. It needs tons of experience, often in simulation first, which can be hard or expensive to get for really complex tasks. It doesn't always learn efficiently.
Okay. So that's where hierarchical learning comes in, breaking big problems down.
Exactly. You have, say, a high-level policy that decides on big goals, maybe using RL or even an LLM. And then low-level policies, maybe using RL or even classic methods like MPC, figure out the detailed movements to achieve those sub-goals.
Like that drone example again, RL figuring out the high-level path through gates and MPC handling the precise flight control.
Precisely. And then there's learning from demonstrations or imitation learning, IL.
So learning by watching an expert.
Right. Instead of pure trial and error, the agent learns from examples of good behavior. The paper mentions a few flavors: behavior cloning, BC, inverse reinforcement learning, IRL, and jail.
Can you quickly unpack those?
Sure. Behavior cloning is the simplest. Just try to mimic the expert's actions directly. Good starting point, but might fail in situations the expert never showed.
Okay.
Inverse RL tries to figure out the goal or reward function the expert was implicitly following. If you get the reward function right, the agent can potentially generalize better.
I see. And jail.
Generative adversarial imitation learning. It's a bit like a competition. One network, the generator, tries to produce behavior that looks like the experts, and another network, the discriminator, tries to tell the difference between the agent's behavior and the experts. They push each other to get better.
The paper mentioned transferring a painting policy to a real robot using BC. That sounds pretty practical.
It really highlights the potential, yeah. Now, let's talk about generative models in single-agent AI. This is a hot area.
Right. Using them for end-to-end control, like a vision language model acting as the robot's brain.
Yeah, directly outputting actions based on camera views and maybe language instructions. Early work used prompts, but now people are fine-tuning these big models or integrating them more tightly with other control networks.
That's for task planning, using LLMs to figure out the steps.
Exactly. Because LLMs have so much world knowledge and reasoning ability, you can give them a high-level goal, like pour water into the cup and put it on the table, and they can break it down into sensible steps.
That's powerful. The review also mentions safety becoming a bigger focus there.
Definitely. You need guarantees these plans are safe and reliable. Generative models are also used in perception, fusing different sensor data, and even reward design.
Reward design, how does that work?
Well, they can either generate reward signals on the fly based on progress, or you could use them to pre-train a model that acts as the reward function itself. Different trade-offs in terms of computation.
And finally, using them for data efficiency, like world models.
Right. Generative models can learn to predict how the world will change in response to actions. That's a world model. Or they can generate diverse simulation environments for training. Both help reduce the need for costly real-world trial and error. Transformers and diffusion models are being used here.
Okay, and to tie the single agent section together, benchmarks, how do we measure progress?
Benchmarks are crucial. Standardized tests, basically. The paper lists quite a few: L for for following language instructions, Robothor for sim-to-real transfer, behavior for household chores, Manaskill 2 for robot manipulation.
OpenX embodiment using real robot data, FizzBench for understanding physics. It's a real mix.
Yeah, it shows the breadth of the field. Different tasks, different environments, sim, real, mixed, different kinds of agents. They're essential tools.
All right, solid foundation on single-agent AI. Now let's pivot to the core topic. Multi-agent embodied AI. The review says you can't just take single-agent methods and apply them directly, right? Things get way more complex.
Way more complex. Suddenly, each agent isn't just dealing with the environment. It's dealing with other agents that are also sensing, thinking, acting, and learning.
That sounds like a recipe for chaos. What are the big new challenges that pop up?
Oh, there's the sheer combinatorial explosion. The number of possible joint actions just blows up. Planning horizons get longer. Then there's partial observability. Each agent usually only sees a piece of the puzzle.
Okay.
And a really tricky one is non-stationarity. Because all agents are learning simultaneously, the environment from any one agent's perspective is constantly changing. What worked a minute ago might not work now because your teammate learned something new.
Like trying to learn tennis when your opponent is also learning and changing their style constantly.
Exactly. And related to that is credit assignment. If the team succeeds or fails, how do you figure out which agent's actions were responsible? It's much harder than in the single agent case.
Wow, okay. So how do researchers even approach controlling and planning for multiple agents?
Early attempts were often centralized. Treat the whole team as one giant system, but that just doesn't scale well. Too many agents, and it becomes computationally impossible.
So distributed approaches, each agent plans for itself.
Right. But then you run into coordination problems. Agents might have conflicting plans or get in each other's way.
The paper mentions grouped multi-agent control. EMPF was the example. What's the idea there?
EMPF stands for Efficient Multi-Agent Pathfinding. The core idea is to dynamically group agents that are physically close to each other. You coordinate tightly within a group, but the groups themselves act more independently.
Ah, like managing platoons of drones instead of every single drone individually.
Kind of, yeah. It balances centralized coordination with distributed execution. It's shown good results for things like large aerial swarms.
Okay, what about learning in these multi-agent settings? The review flags specific interaction challenges, asynchronous collaboration.
Yeah, that's when agents aren't perfectly synced up. Maybe there are communication delays, or some agents compute faster than others. They might act or get feedback at different times.
How do you learn effectively then?
The paper mentions ACE, which uses macro actions, basically, shared high-level goals for the team to help coordinate learning. And MAPIO, an algorithm adapted for handling delayed feedback in multi-agent settings.
Another challenge, heterogeneous collaboration. Agents with different abilities.
Right. Imagine a delivery drone working with a ground robot. Or different types of self-driving cars. They have different sensors, different ways of moving, maybe even different goals that contribute to a larger team objective.
So you can't just use the same learning algorithm for everyone.
Not easily. Approaches like HGPPO or COMAT use separate neural networks for different agent types, but connect them with graph-based communication structures. And again, credit assignment becomes even harder here, figuring out who contributed what when agents have different roles and skills.
And then there's self-evolution in open environments. This sounds like the real Wild West. Real-world unpredictability.
Exactly. Not a control simulation anymore. The environment changes, tasks change, maybe even the agents you're working with change over time.
How do you train for that?
It requires more robust approaches. Things like training policies specifically to handle unexpected events, methods for continual learning so agents can adapt without forgetting old skills, using advanced architectures like GNNs or transformers that might be better adapting, and even self-play where agents learn by competing against or collaborating with versions of themselves.
Now let's bring those generative models back in. How are they being used specifically for multi-agent systems?
One big area is task allocation. An LLM, with its broad knowledge, can look at a complex team goal, break it down into subtasks, and assign those tasks to different agents based on who's best suited.
Smart's LLM was mentioned.
Yeah, that's an example where the LLM does the task decomposition and agent grouping. There's also work on integrating the assignment directly with execution planning, maybe using graphs to show task dependencies.
And for collaboration itself, can LLMs help agents work together better in real time?
Potentially, yes. The idea is agents could use LLMs to sort of negotiate or discuss the best course of action. The review mentions iterative rounds of communication, maybe even dynamically changing team roles based on these negotiations.
What about humans in the loop? Human AI coordination.
That's a huge goal. How do we get humans and AI teams working together smoothly? Some research uses multi-LLM setups almost as stand-ins for human partners to study the dynamics. But the real focus is on active human involvement.
Like the AI asking for help when it's unsure, or trying to figure out what the human wants.
Exactly. Seeking guidance, inferring intent, making the AI a better teammate for humans.
And finally, data efficiency again, using generative models like world models, but for multiple agents.
Right. The challenge now is modeling not just the environment, but the interactions between agents. Early work did this for small teams. Now, generative models are helping fuse observations from multiple agents, predict joint trajectories.
The review mentioned traffic simulation and diffusion models for shared environment understanding.
Yeah, using generative models to build shared world models or predict complex multi-agent dynamics seems really promising for training more efficiently.
Okay, and benchmarks for multi-agent AI. The paper says this area is a bit less developed.
Relatively speaking, yes. Compared to single-agent benchmarks, multi-agent ones are fewer and often more specialized.
We saw examples like GridMAPF for path planning, SMARTS for autonomous driving,
Megaverse for diverse tasks, BiDEX for manipulation with different robots, Lemma for language-driven multi-robot stuff, CHI for social collaboration, PartNR for human AI language collaboration.
So still a growing collection, but maybe not as comprehensive yet.
Exactly. The review sees them as important for mapping the field and showing where the gaps are. There's still work to do in creating really general, challenging, multi-agent benchmarks.
Which leads us nicely into the final sections, the big challenges and future directions. What are the main roadblocks the review identifies?
Number one is probably effective and efficient learning. That combinatorial explosion we talked about makes learning incredibly sample inefficient. Agents might need way too much experience to learn good collaborative strategies.
So what are the potential fixes?
Better world models could help agents plan more effectively. Smarter exploration strategies to avoid wasting time. Using imitation learning to get a head start. Meta-learning to generalize better across tasks. And critically, getting better at sim-to-real transfer and multitask learning.
Makes sense. Challenge number 2, adapting to open environments. The messy real world again.
Yeah. Dynamic conditions, uncertainty, unexpected events, non-stationary behavior from other agents or humans, changing tasks. It's tough.
What's needed here? Robustness, continual learning.
All of the above. Policies need to be robust to noise and surprises. Agents need to learn continually without catastrophic forgetting. They need contextual reasoning, understanding the current situation, and the ability to switch strategies quickly when things change. Lots of research, but still major challenges.
And the third big one, evaluation and verification. How do we know these systems actually work reliably and safely?
This is critical. The review argues current benchmarks often aren't complex or realistic enough. They might focus on single types of sensors, assume perfect communication, or use small, homogeneous teams.
So we need better benchmarks.
We need more general, modular, scalable frameworks, ones that handle multimodal data, heterogeneous teams, realistic communication issues. We need standardized metrics, reproducibility, and probably more physical test beds for validation, especially for safety.
And all this effort is driven by potential applications, right? The review lists quite a few.
Oh yeah, huge potential. Robotics, autonomous driving, education, healthcare, military, simulation, smart cities. The list goes on.
But each area has specific needs.
Absolutely.
Yeah.
You can't just drop a general multi-agent system into a hospital setting. You need domain expertise, rigorous validation, safety protocols tailored to the application.
Finally, the paper points to some other future directions that maybe haven't gotten as much attention yet.
Right. Things like better multimodal perception, really integrating vision, sound, language, touch effectively for teams, more sophisticated collaborative learning protocols where agents can actively teach each other.
Social learning for emergent intelligence. That sounds fascinating.
It is. How do complex group behaviors arise from simple local interactions? There's a lot we don't understand theoretically yet, and, crucially, safety and ethics. As these systems become more autonomous and capable, we urgently need clear guidelines, ways to enforce constraints, and methods for making their behavior understandable and trustworthy.
So wrapping this all up, this deep dive guided by the Feng et al. Review paints a picture of multi-agent embodied AI as a field that's, well, really taking off.
Absolutely. It's building logically on single-agent foundations. incorporating powerful new tools like deep learning and generative models, and tackling these incredibly complex interaction problems. The progress is genuinely exciting. We're moving towards AI that can physically collaborate.
But as we've discussed, it's not smooth sailing. Those challenges, learning efficiency, real-world adaptation, robust evaluation, there's significant hurdles.
They really are. And they represent the frontiers where a lot of the current innovation is happening. Solving these is key to unlocking the full potential.
Which brings us to a final thought for you, the listener. Thinking about this capability, AI agents truly collaborating, physically interacting in our world, how do you see that reshaping things, industries, daily life?
What are the really surprising implications, maybe the ones we aren't even thinking about yet, of having truly intelligent, embodied teams of AI operating alongside us? Definitely something to ponder. We'd encourage you to check out the paper itself and maybe explore some of those benchmarks we mentioned.